Okay, so here's where we were last time. So we were talking about bases, and specifically how to use bases to find something called coordinates for a given vector. So this is a flashback. Oh, before I get into that, let me just remind everybody about the attendance quiz and the attendance code. There it is on the board. Do make sure to fill out your attendance quiz sometime during the lecture, or 5 minutes before, 5 minutes after, the usual. Okay, so the reminder, a basis allows you to take, by way of this construction of linear combinations, a basis allows you to take a vector in the vector space and infer a corresponding list of coordinates. Right, and the notation we use to represent this is, given a basis, the vector's coordinates with respect to that basis are these numbers, like that. And so specifically this notation with the square brackets or the subscript indicating the basis is the notation for the coordinates of that vector with respect to that basis. Okay, so this is just a rewrite of something that we talked about back in chapter 2 somewhere. I want to say 2.4, I think it was. But we're going to start doing a lot of stuff with this now. So before we go on, what I'd like to do is give you a couple of different points of view on how to think about this. Right? So in chapter 2, our point of view was if you give me one vector, then I can get from that one set of coordinates for that vector. Okay. So I'm going to reinterpret this now as a function, as follows. If you give me a vector in a vector space, got ahead of myself. Let's suppose we fix a basis. Fix a basis. Right? This basis allows us the following situation. If you give me a vector in a vector space, then I can play the above game and infer a list of coordinates, namely a list of numbers, an ordered n tuple, namely a vector in Rn. Okay, so effectively then a basis can be thought of as a function. This is a very different point of view than we took back in chapter 2. Right? Thinking of a basis now as a function. Vector in, coordinates out. Now, why would we be interested in doing such a thing? Well, turns out we're going to see a lot of different applications of this idea. It will take us a while to get to those applications. Hopefully it's no surprise given the title of this course, but one of those applications, believe it or not, is that we're going to be able to use this as a necessary tool as part of solving a bunch of differential equations. It's really hard to see it coming, but this is going to be a very important part of that process. So a very new though interpretation. Yes, a basis is a list of vectors that has certain properties. Right? The new interpretation that I want to push is that a basis is a function. Why is this a useful thing? Well, a couple of plausibility arguments. Vectors in a vector space come in many different shapes and sizes. We've seen some pretty wacky vector spaces, right? Not only are they individually wacky, but they're individually very different from other individual vector spaces. So this is a big tent of weirdos. We're talking about abstract vector spaces, right? In each one, pick a basis, and we can talk about all of them in this very consistent, very compact way of coordinates with respect to a basis. Okay, so that's really nice. Okay, now here's a different point of view I want to give you on how to think about a basis. It is a function, and that's nice. This other point of view, I would like to encourage you to think of a basis as being kind of like a language, which sounds weird, but I think this is a very strong analogy. Okay, a basis is kind of like a language. So let me remind you, what is a language? A language is different points of view you can take, but I'm going to observe here a language you can think of as a bunch of conventions of convenient labels that we put on things that are otherwise hard to talk about. So, for example, suppose I want to talk about this thing here, okay? This big thing. Well, I could, every time I want to communicate that I want to talk about this thing, I could, I suppose, whip out a piece of paper and draw a picture of it and say, that thing, right? That's tedious, clunky, slow. How about we just give it a name, desk. Right? Much easier to just, let's come up with a label. We'll associate a very easy to remember label to describe this abstract concept, and then I don't have to draw pictures constantly. Right? Okay. That's kind of what a basis is doing here, right? We just got through talking about how vectors in vector spaces, some kinds of vector spaces are weird and full of oddball vectors. Furthermore, there's a lot of different kinds of vector spaces. You might get used to talking about vector spaces of functions, but then at a later date find yourself needing to talk about vector spaces of matrices or vector spaces of, I don't know, colors. Who knows, right? So weird, hard to describe things, you can think of coordinates with respect to a basis as being convenient labels that we stick on them, right? It is always convenient to just write down an ordered n-tuple of numbers, a comma b comma c. That's easy, and always the same format. Very nice. So, again, I think the analogy with languages is very strong. I will use that pretty regularly during this the rest of this course. We're going to be, by the way, I'll give it away, but we're going to be using the idea of coordinates of a vector with respect to a basis a lot in the remaining however many weeks we have in this course. So instead of referring to the coordinates as, these are the coordinates that describe the vector v with respect to the basis script v, very often what I'll say is this vector in script v language is these numbers. And it just kind of rolls off the tongue nicely. And again, intuitively, that's how I think about these coordinates. These coordinates are just a convenient label that we put on this abstract, potentially hard to discuss vector. Okay. So I encourage you to think about that language point of view on what's happening here. By the way, here's another analogy. We know that different languages give you different names for things. Like, so this is, desk in English, and there's going to be some totally different word for how to describe this thing in, I don't know, Japanese or something, right? So different languages, different convenient labels for a given thing. Well, the exact same thing happens here. If you change to a different basis, let's come up here and look at this formula. If you want to describe some abstract vector v, well, given a certain list of basis vectors, there's going to be a certain list of coordinates. But if you change to a different basis, if you change these purple vectors to a completely different list of vectors, well, no surprise, you get completely different coefficients, namely completely different coordinates. So the analogy works very well with different bases as well. Different bases give different labels, just like different languages give different names. Anyway, I'm a big fan of this language metaphor. Okay, a couple of quick examples. So let's talk about this vector space, P2, vector space of polynomials at most degree 2. Let's think about this basis, script v, for that vector space. And let's think about the following vector, f. That vector f is a vector in the vector space. If I wanted to describe that vector, now it's a function, right? If I want to describe that, then capitalizing on the fact that, well, I've got this given basis, v1, v2, v3, and I can write it as a linear combination of those basis vectors with these coordinates, then I can say that the coordinates of that vector with respect to that basis are 3, 3, and 11. So now again, different ways you can read this. You can say f, its coordinates with respect to the script v basis are 3, 3, 11. Here's a different way that you can say this same statement. You can say f in v language is 3, 3, 11. See how that rolls off the tongue a little more nicely? Anyway, that's just me making my own personal sales pitch. Here's another way you can say morally the same thing. By the way, let me come back over to here and talk about a notation before I get to that last thing. Notice that the basis, the thing that we're using to convert a vector into a list of coordinates, the notation that we're using is to square brackets, basis as a subscript on the right. That's the book's notation. It's a very common notation. I like it. We're going to use it. Here is a different thing that you can do. You can go the other way. You can say, suppose I have a list of coordinates. What is the vector that has those numbers as its coordinates? Well, the vector that has those numbers as its coordinates you denote by putting the basis on the left. That notation is not in the book. I made that up for Math 216 purposes. Different books, different contexts use different notations. I think this is a reasonable choice. Subscript on the right when you're going to the right. Subscript on the left when you're going to the left. Okay, anyway, with that in mind, that gives us a third way to describe this statement right here, this statement about how f is a certain linear combination of the basis vectors. F's coordinates with respect to the script V basis are 3, 3, 11. F in V language is 3, 3, 11. Or, if you like, F is the 3, 3, 11 linear combination of the script V vectors. So all of those enunciations that I just made, all really morally, they all say this same statement right here. Those all say the same thing. Okay. Alrighty. The next example is morally equivalent. The thing that's a little weird about this next example is that the vectors in the vector space that we're describing are just vectors in R3. So there's something weird, something kind of confusing, a little bit conflating maybe in this next example, that the abstract vector space is R3, and the labels we're going to put on those abstract, on the vectors in R3, those labels are also vectors in R3. So it's easy to get confused on, wait a second, is this a vector or is this a label? Are these coordinates or is this a vector? It can be confusing. So here's what we're doing. We have this basis. We're going to write vectors with in terms of coordinates with respect to that basis. Here's a vector. You can check for yourself that it's this linear combination of those basis vectors. Multiply it out. Okay. And so two ways to say that. This vector's coordinates with respect to that basis are these numbers. That'd be one way to say it. Or alternatively, this vector is the 4, negative 2, 1 linear combination of those basis vectors. So take your pick. All three of these statements say the same thing. Okay. All right. Okay. Now, let me come back up to where we were over here. Reminder that what we've got here is a basis serves a role as a kind of a function. It takes abstractions, in this case vectors, and turns them into something pretty concrete. I mean, there's lists of numbers, right? Abstract vectors in an abstract vector space. We turn it into a list of numbers. Thank you, basis. All right, so the question I'd like to ask is, if a basis, as it did here, can turn abstract things into, convenient, numerical things, are there other kinds of abstractions that we can do this with? Can a basis help us turn other ugly abstractions into numerical objects? Yes?
So when you say it turns, like, the ugly vector into, like, a better looking, like, in this example, it just changed the the number in the vector, right?
Yeah, so in this example here, it's hard to see the advantage because we turned a list of numbers into a list of numbers. But let's look at this example here. Here we turned a function into a list of numbers. Now, you may say, and sure, fine, that function's not that hard to write down, right? But I made this example kind of deliberately not that unwieldy because I didn't want to have to write down a bunch of unwieldy things. But you could use your imagination and imagine that maybe I might have a really ugly vector space of functions that are really hard to write down, right? In which case, being able to rewrite an ugly thing as a list of numbers is pretty handy. Does that make sense? Yeah. Okay. All right. Okay. So a basis has allowed us to turn an abstraction into something numerical. Let's try to do that in other contexts. Here's what I'm talking about specifically. Suppose we are talking about a linear transformation. Linear transformations are, it's an abstract concept. There's lots of different kinds of linear transformations. We've seen some pretty weird ones, right? And that's not convenient, right? So wouldn't it be nice? Mightn't we be able to somehow use bases to turn abstractions somehow into some sort of a numerical construction in a canonical way, something convenient to work with that represents the linear transformation? Okay. So turns out we can. What we're going to need is a basis for the domain. We're going to need a basis for the target. We're going to need two bases in this case. And with these two bases, I'm going to be able to turn this abstraction of a linear transformation into something nice and numerical and convenient. We'll see what we get in a couple moments. Here's how it works. Let's just represent what we've got. Don't forget what a basis does. Script V, being a basis for the vector space V, is a way of converting vectors into coordinates. Right? That's what a basis does in the vector space V. Script W is a way of turning vectors into coordinates in the vector space W. Again, that's what a basis does. And don't forget, the abstraction that we're trying to deal with here is a linear transformation from V to W. Now, altogether then, what we have, starting in the bottom left corner, we have a linear transformation followed by a linear transformation followed by another linear transformation. Altogether then, this composition is a linear transformation from Rn to Rm. And where have we heard that phrase before? There are only so many linear transformations from Rn to Rm, and we made this very powerful observation early in section 5. The very first thing we observed in section 5.3 was that a linear transformation from Rn to Rm is a matrix. And we even came up with a formula for how to write down those matrices. Remember, we had the little cheat phrase was the columns are the images of the standard basis vectors, right? That's your formula that tells you how to take such a linear transformation. I like to call these Euclidean linear transformations, Rn to Rm, and how to represent it with a matrix. So, so this thing here is a matrix. And we can represent it, literally with a matrix. And that, by the way, is a numerical thing, right? It's not a list of coordinates. When we were dealing with vectors, the numerical object that we represented things with respect to was just lists of coordinates. Here we get an array of numbers instead of a list of numbers. Nevertheless, highly numerical. It's just a bunch of numbers. Okay, so we have used bases successfully to turn an abstraction into something numerical. Okay. All right, a little bit of notation. The linear transformation that you are representing, you put inside of square brackets. Now, let me go back up here to where we were talking about vectors. The abstraction that we're representing, we put inside of square brackets. Right? This is just like we did with vectors, abstraction inside of square brackets. Then we put a basis indicating, what basis are we converting it with. Right? So here the basis was script V. Make that a subscript to get our list of coordinates. We're going to do something kind of analogous down here. Now it's got to be a little bit different because here there are two bases. There's the input basis, script V. We're going to make that a subscript basis. Then there's the output basis. And we're just going to make that a superscript. This is the notation that the book uses. It's kind of arbitrary. By the way, different books make different choices of how to, which bases go where. I've seen books where the input basis is a subscript on the left, output basis is a subscript on the right. I've seen it the other way. There's lots of different ways to do this. We're going to stick with the book's notation on this, just for consistency, compatibility. Input basis, domain basis as a subscript on the right. Output target basis as a superscript on the right. Okay, so those are the objects that we need in order to write the corresponding matrix. So that's the notation that we'll use to represent that matrix. How are we doing? Is everybody on board? Questions? Okay. All right. So keep in mind what we've got here. We've got this abstraction that this is a linear transformation that takes inputs and gives outputs. We're representing it with a matrix that I'm thinking of as likewise taking inputs and doing outputs. Roughly speaking, what I'd like to say is the linear transformation and the matrix kind of do the same thing. Roughly speaking, the matrix is it's not exactly the same because it's numerical linear transformations and abstraction, but they're kind of doing the same thing. And here's what I mean by that. If you look at this equation down here, the linear transformation is doing the same thing as the matrix in a certain sense. Now, there's a couple of details we need to talk about, but notice what this is saying is the linear transformation applies to V. This matrix kind of sort of applies to V, sort of in a sense also. Okay, now the little detail devils. The matrix doesn't technically quite apply to V. Of course it doesn't. The matrix is an array of numbers. The vector V is an abstract thing. It's an abstract vector. So the matrix is acting on not technically V itself, it's acting on the notation that we use to represent V, the coordinates that we use to represent V, with respect to, of course, the input basis, because this is a vector in the input space. Right? So really, what we're saying here, this thing here is saying what the matrix does, okay, fine, what the matrix does to the coordinates of a given vector, not the vector itself. Now let's go back to the left side of the equation. The linear transformation T, that applies directly to the vector. Sure, yeah. But we don't stop there. If we want to compare this to what the matrix does, notice the matrix is going to spit out a bunch of coordinates. It's going to spit out coordinates in W language, right? T is going to spit out a vector, an abstraction in the W vector space, right? So when I say that these are the same thing, what I mean is that the output of T thought of in W coordinates, right? So all together, we do T and then think of the output in W coordinates. So this is really what I mean when I say that the linear transformation and the matrix do the same thing. They do the same thing, interpreting accordingly as appropriate between vectors and coordinates representing those vectors. Okay. In the diagram, what this means is down and over is the same as over and down. Interpret the ups and downs as just that's just converting. That's just different ways of thinking about the same thing. Other than a couple ups and downs, just to kind of dot your I's and cross your T's. Across the top is the same as across the across the bottom. Okay. All right, now I want to show you, let's get our hands dirty kind of example. So I'm going to make up a linear transformation. I'm going to make up some bases, and I just want to show you what I mean by a matrix representing that linear transformation. Here is my my made-up linear transformation. Y'all will recognize this guy. Differentiation. The act of differentiation is a linear transformation. We proved this is linear a while ago. Okay. Now notice I've confined our attention to a very specific vector space here, P3. So we're not considering all differentiation. All the rules that you learned back in Calc 1, the quotient rule and the product rule and all those trig rules and exponential rules and oh my gosh, right? So no. This is just on P3 polynomials, at most cubic polynomials. And you get right down to it, the act of differentiation on polynomials is a pretty simple process. There's only so many kinds of terms, right? Okay, so I'm going to have to pick a basis for my domain. Here's the basis I'm going to pick. There are, of course, many bases. I picked this one mostly out of convenience. You could pick a different basis. There would be all the subsequent details would be different in the example. I picked this one arbitrarily. Likewise, in the target, I have to pick a basis. I'm going to pick this basis for the target. So notice, just like in our setup, I have a linear transformation, I have an input basis, I have an output basis, and I want to know what is the matrix that represents that linear transformation with respect to those chosen bases. All right, now I claim it's this. I claim that this matrix does it. That matrix, believe it or not, that is a surprisingly simple matrix. This represents the act of differentiation on that vector space in the language of this input basis and in the language of this output basis. Two questions that you should be wondering about. First of all, where in the world did I get this from? I pulled it out of thin air for the moment. Right? I will show you the formula for how to get that. I will explain exactly how to motivate, how to get this formula. We'll do an example a little bit later on. For the moment, I just want to kind of get our hands dirty and see how this is used. Right? The next question is, do we even believe that this is right? Right? So what I'm going to do is I'm going to start off with a sanity check, what I like to call a sanity check. Let's just try one. Let's see, does this do in any examples what I claim that it does? Okay. All right. So, okay, what do I claim this does? Well, here's our picture. So keep in mind this is our linear transformation. That's our differentiation. I've got a basis here for the domain. I've got a basis here for the target. My claim is that matrix executes the differentiation for me. So let me say that a little bit differently. What I really claim is that down and over should do the same thing as over and down. That's my assertion. And I'm going to confirm that that's the case by I'm going to pick an actual vector out of there. We're going to look at that one. This is just a sanity check, right? This isn't going to prove anything. But just a plausibility argument. Let's take this kind of arbitrary vector here, x squared plus x. Let's go down and over. Let's go over and down. In other words, let's do the differentiation. Let's multiply by the matrix appropriately in coordinates, of course. Right? And let's just see, do we get the same thing or don't we? This is a very straightforward process at this point. We'll start with over and down. Here we go. Over and down says step one, take the derivative. This is an easy derivative. It's good old Math 111L derivative. Get 2x plus 1. Next, I've got to figure out how to write 2x plus 1 in coordinates. Now, we've got to be careful. we're writing 2x plus 1 in coordinates with respect to W. Reminder, what is W? What is script W? Script W, the basis for our target, is this, x squared, x, and 1. So I've got to figure out now, looking back at 2x plus 1, how do I write 2x plus 1 as a linear combination of these three vectors? Now, it's a little, got to write it down, multiply it out, equate the coordinates, say if you wanted to sort of brute force it. But I appeal to your sort of algebraic intuition here. 2x plus 1, you can just see it coming. There's none of these. There's no x squareds in 2x plus 1. Then there's 2 of these and 1 of those. Right? So if I were to take the 0, 2, 1 linear combination of these vectors, I get the 2x plus 1 that I'm interested in. And so here you go. This 2x plus 1, its coordinates with respect to W, 0, 2, 1. Okay, so over and down gives me 0, 2, 1. Is everybody on board so far? Okay, our assertion is that over and down will be the same as down and over. So now let's go down and over. What I'm going to have to do again is convert and then just follow the instructions here. This says first find coordinates with respect to V. Reminder, what is script V? Script V is that. Right, so for the first part of what we're doing here, for the sort of the down part, I've got to figure out how to take this vector x squared plus x. How do I write x squared plus x as a linear combination of our script V vectors? Well, let's see here. X squared plus x, and again, in general, you might have to kind of write it out and equate coefficients or something. But x squared plus x, here they are, right? No x cubes, 1x squared, 1x, and no 1s. And so 0, 1, 1, 0, that linear combination of these basis vectors gives us our x squared plus x. Okay, so 0, 1, 1, 0 are the coordinates. Multiply by the matrix on the previous page. 0, 1, 1, 0 times that matrix here. Multiply by 0, 1, 1, 0. And you get 0, 2, 1. And as required, notice we get the same thing here. So over and down is the same as down and over. Said differently, in the appropriate, understanding with respect to the appropriate languages, the act of differentiation is executed by the multiplication of that matrix. How are we doing? Questions? All right. Okay. All righty. Now, again, this was just a sanity check. Here's what I think would be a nice exercise. I did this calculation for x squared plus x. Pick some other at most cubic polynomial. Go through the same process. Confirm for yourself. Try to make it fail. And it's never going to fail. No matter what polynomial you start with here, the active differentiation is going to be effectively achieved by the multiplication by that matrix appropriate to coordinates in the same way that we just talked about here. It's always going to work. It's pretty surprising. Okay. All righty. So now the big question, where did I get this from? I pulled it out of thin air. Seems to work. How did I do that? Do you have to just consult your inner oracle every time? No. There is a nice formula for how to do it. I'm going to show you the process for how to motivate the formula. I think this is a nice argument. It's a good exercise this is a little bit of mathematical weightlifting. We could just write down the formula, but I think it's a healthy exercise to see how this came about. We're looking to figure out how to represent that matrix. What does that matrix do? That matrix is a linear transformation from Rn to Rm. We know about linear transformations from Rn to Rm. Neat facts that we know about linear transformations from Rn to Rm. That is, the columns are the images of the standard basis vectors. Right? So you remember that from the very start of this very long section that we're now in the middle of. So the way I'm going to compute this matrix is literally one at a time. I'm going to look at the standard basis vectors inside of here, and I'm going to see what their images are. And I'm going to make those the columns of my matrix. That's it. The columns will be the images of the standard basis vectors. Okay, so that's what I've got right here. The columns are the images of the standard basis vectors. Let's see here. The columns are the images of the standard basis vectors. That's what that math says right there. Yeah? Okay. All right. Quick observation. That, the multiplication by that matrix, this matrix I'm trying to find, is the same as that. Up and over and down. And up and over and down is something that I can write down explicitly. There it is. That says up and over and down. Now let's walk through and make sure that we see how that process that this does up and over and down. We're starting with a standard basis vector in Rn. Let's see here. Oh gosh, I need some color. Okay, fine. So up, we're going to find the corresponding vector in the vector space V. Over, we're going to apply the linear transformation, T. Down, we're going to write the result of that in coordinates with respect to script W. So it's getting to be a little bit of a weird thing to write down, but nevertheless, here's the algebra for how we represent up and over and down in that diagram. So don't get intimidated by the weirdness of the notation. Okay, so let's go through this process. We're going to focus most of our attention on the act of taking a list of coordinates and you know what? I made some weird color choices here. Of taking a list of coordinates here. Oh, here we go. A list of coordinates and how to write what is the corresponding vector in V. How do I find this vector? I would like to know what is the vector that I get when I take a linear combination of the script V vectors so something times V1 plus et cetera, plus something times Vn. I'm going to take a linear combination of those basis vectors V1 through Vn. Here are my coordinates. My coordinates in Rn, standard basis vector. That's a bunch of zeros. Right? Remember these vectors, EI. This is a bunch of zeros with a single 1 in the ith position. That's our definition of a standard basis vector. So the linear combination I'm taking here is a bunch of zeros, but then there's an extra term. There's one single term in here where there's in the ith position, this being the ith term, in that ith term, my coordinate is 1. Right, so that's taking the standard basis vector in Rn, EI, and taking that linear combination of the script V vectors. That's what this algebraically is. And notice that it's really easy to write down a formula for this green vector. This green vector that I'm looking for, well, gosh, most of these terms go away. The only term that doesn't go away is that one. It's 1 VI, otherwise known as VI. How are we doing? Everybody follow that calculus? This is just explicitly following the rules for what does this notation mean. How to turn a list of coordinates with respect to a basis into a corresponding vector in the vector space. Okay, and believe it or not, we're actually done now. This calculation gives us what we need. Here then is the formula that we're going to work with. If you would like to understand a matrix representing a linear transformation, we're going to understand it one column at a time. Each one of those columns we're going to compute by taking input basis vectors, doing the linear transformation to those input basis vectors, and then whatever comes out, we're going to write in W coordinates. Okay, so now let me show you how I sort of think about that. So this matrix that we're trying to understand here, we're going to take our input basis vectors, we're going to stick them into T. Whatever comes out of T, we're going to write with respect to the output basis. So these go in there, and then we write the results in that language. Easy way to remember the process. Let's get our hands dirty and do one, see what this actually looks like. Let's recall our previous example. We're looking at the linear transformation is differentiation. Here's our input basis. Here's our output basis. We're going to follow this rule. Take the input basis. We're going to do the linear transformation, write the results in output language. And here's how that plays out. Here's that input basis. Those were the input basis vectors, V1 through V4. They were x cubed, x squared, x, and 1. Here we do the linear transformation to them. In other words, this linear transformation was just take the derivative. So we're going to take the input basis vectors, we're going to take their derivatives. That's easy calculations, right? Those input basis vectors, we can just math 111L, take their derivatives. You get 3x squared, 2x, 1, and 0. Lastly, again, following the formula, input basis vectors, do the linear transformation. Last step, write the coordinates with respect to that target basis, script W. Our target basis was x squared, x, and 1. Let's write those derivatives with respect to x squared, x, and 1. And it's just a matter of, thinking them through. So, for example, this 2x. How is 2x a linear combination of x squared, x, and 1? Well, it's 2 times the x vector. There's no x squareds in here. There's no 1s in here. So it's 0x squared plus 2 times x plus 0 times 1. And so you get these coordinates. Those coordinates are those numbers. Let me write that out. 2x is 0x squared plus 2x plus 0 times 1. So these were the basis vectors. Here then are our coordinates, 0, 2, 0. Everybody happy? Okay. All right. Now keep in mind, well, what was the deal? Why did I just do that? Why did I just take these vectors and stick them into there and take what comes out and write in that language? The reason I did that is because those are the columns of my matrix, right? So having computed those several lists of coordinates, those then become my columns. So you can see that right here. These coordinates become these columns, and there's my matrix. There's the matrix that represents differentiation, and you'll notice this is the exact same matrix that I, pulled out of a hat when we first did this example. This is how I actually computed this matrix in the first place. Okay, pause for questions. How are we doing? Okay. Oh, yeah. Uh-huh.
If you're like transforming to something with different dimension, you're going to have columns and zeros.
Let's see here how to say that. No, not necessarily. So there was something nice about differentiation that happened here. The derivative of 1 is just 0, right? That was a kind of coincidence. In general, linear transformation need not have nice coincidences like that. So there's no such showing. Yeah. Anybody else? Great question. Anybody else? Yeah.
We can only do this for finite dimension.
Yes, finite dimensional domain and finite dimensional target. That's right. Yeah, absolutely. All right. Okay. So a couple of quick related examples. You'll notice in this example here, we started with, let me go back to here. We started with a linear transformation that was given, and the question was, how do I find the corresponding matrix? Given the linear transformation, what's the matrix? What if it comes the other way around? What if somebody says, here's a matrix representing the linear transformation? What does that tell me about the linear transformation? Right? So let's look at this example here. Suppose that I know, for example, that the matrix is this, but I don't know T. How do I infer from the matrix something about T? Ultimately, the answer is write down all the same formulas and just interpret them backwards. So, for example, let's write down, what does this column here tell me, that column 101? Well, I get that first column by taking the first vector in there, plugging it into there, and then writing the output in that language. Let me write that down. Starting with the first input vector, V1, doing T to it, and then writing the output in W language. And then I just make the innocent observation that, of course, this statement, let's see here, equals 101, so that's where this 101 came from. That statement is equivalent to this statement. Right? So the W coordinates of something being 101 means that that thing is the 101 linear combination of the W vectors. And as required, we've learned something about the linear transformation. So we were given the shorthand, we were given the matrix, and now I know at least something about the linear transformation. And of course, you can do the same kind of thing in the same way that this column tells me that. Well, likewise, that column tells me that, and this column tells me that. In fact, now I know what the linear transformation T does to several vectors. Furthermore, I know what T does to a basis's worth of vectors. And then by linearity arguments, I can compute what T does to any vector. So effectively, this is a way of telling me what the linear transformation is, however, perhaps a little awkwardly. Okay. All right, so there we go, sort of working it backwards. Everybody on board with this calculation? Okay. All right. This example here is really the same. I'm just going to make one quick observation about this, that here I'm presuming we use the same basis for the domain and the target. Now, there is an immediate consequence of that. If we're using the same basis for the domain and the target, that means the domain and the target are the same vector space. So this situation implies that we're looking at a linear transformation from V to V. It's got to be, the target can't be something different like W. It's got to be the same because we're using the same bases. Right? Okay. All right. And just a little bit of foreshadowing. It turns out that this matrix is of particular interest. It's going to be an important matrix that we'll talk about in section 5.5. It is important because of ultimately, something really nice about these equations that we'll again see later on. Okay, and let's see, how are we doing? Are we, yeah, we're out of time. Okay, all right. Stop there. Y'all have a great weekend. See you on Monday.